In this video, we're going to explore the mechanism for the dissolving metal reduction of alkynes. This is a new kind of mechanism for us in that we are using what's called a radical here. This has an unpaired electron. Making it a radical. That's a new word for us. So mechanisms involving radicals, we have to have a new way of showing the one electron reacting, and here's how we're going to show it. Right here is what we call a hook. It's not an arrow, it has only half of an arrowhead. Looks more like a fish hook. And it represents the flow of one electron in a mechanism, and we will use that in our mechanism right now. We're going to explore the reduction of 3-hexyne using sodium in ammonia to make trans-3-hexene. We're going to start with a hook. Sodium is going to provide a hook towards one of the carbons. This hook indicates that that single electron is going to be deposited on this carbon here. Now, carbon would have an octet violation if that was the case, so we must compensate by breaking this pi bond in half. One half of it going towards the pink hook, creating a lone pair, and the other half towards the other carbon, creating a carbon radical. And those hooks will look like this. One second. This hook combined with the hook on the right to create a lone pair, and this hook created a radical on the left, and that would look like this. The species we have generated here is called a radical anion. It should be noted that the anion portion of the radical anion is the conjugate base of this alkene right here. Alkenes have a pKa of 45. This has a pKa of 40. It is the same pKa as an amine. 40 always goes towards 45, so our next step is simply an acid-base step. These are normal old reaction arrows indicating pairs of electrons flowing in a normal mechanism, giving this result here. So we've used 1 mole of our ammonia. It's not like ammonia is going to run out when it's the solvent. And we've generated a carbon-hydrogen bond that we need, and we have a radical. To put the second hydrogen on, we need the carbon to look more like this carbon here, which means it needs 1 more electron. One thing I did not mention is that sodium is actually in excess. There are at least 2 moles of elemental sodium in there, so we should feel free to use a 2nd mole of sodium, and it will provide a 2nd electron in a lone pair, creating this intermediate here. This anion is the conjugate base of our final product. All that remains is an acid-base mechanism with another molecule of solvent. Lone pair makes bond, creating the pKa 45 right here, and thus finishing our mechanism. We used 2 moles of sodium. Each time we created sodium cation. I didn't show that either. First sodium cation generated in the first step. Next sodium cation generated here. And we also made 2 molecules of amide ion, NH2-. One of them in this last step, and one of them right here. And you're probably dying of suspense to figure out what this yellow box is hiding. Anti-stereoselectivity leads to transalkenes. We have a transalkene here. The reason we have anti is when we formed this radical anion, we wanted the radical as far apart from the anion as possible because electrons really don't like each other. And to do so required an anti-arrangement of the electrons. I hope you have found this video on the dissolving metal reduction of alkynes to be useful, and I look forward to our next video.